Good morning, everyone. I'm here to share the last lecture for organic chemistry, but this is not the last lecture for A-level chemistry syllabus. I still have electrochemistry and the periodic table. So after this last organic chem topic, I'll be moving on to periodic table first, transition metal, and then electrochem. So this lesson is going to be quite long, will be double the length of last lesson on carboxylic acid. It's about 40 pages. The previous one is about 20 plus. So there are quite a number of concepts we're looking at and some examples to work out, like the concepts of amine, amide, amino acids, and finally proteins, which will end our A-level chemistry syllabus. So there's quite a lot of learning outcomes to achieve. Okay, let's start with amine. They are derivative of ammonia, where one or more hydrogen atom of ammonia molecule was substituted by alkyne or aryl groups. Amines can be classified as primary, secondary, or tertiary amines depending on how many alkyne or aryl groups attached to the nitrogen atoms. Okay, so we have ammonia, followed by primary amine, secondary amine, and tertiary amine. In the common name of amine, the name of the alkyne or aryl groups bonded to nitrogen are given first, followed by the suffix amine. So we have aliphatic amine and aromatic amine. So for aliphatic amine, for primary amine, the examples include methylamine, ethylamine, 2-propyl amine. All right. As well as ethane 1,2-diamine, phenyl methylamine. For secondary amine, we have ethyl methylamine, okay, as well as diethylamine. Tertiary amine include dimethylethylamine or trimethylamine. Okay, so if you have only one hydrogen bonded to the nitrogen of the amine, is secondary. If no hydrogen, tertiary. 2 hydrogen amine, primary amine. For aromatic amine, they are amine in which the nitrogen atom is directly attached to the aromatic ring, like phenylamine or 2-methylphenylamine for primary amine. For secondary amine, we have N-methylphenylamine or diphenylamine. For tertiary amine, we have N,N-dimethylphenylamine. Okay. So in naming amine with more complicated structure, or in compounds in which other functional groups are of higher priority, NH2 becomes the amino group. For example, the carboxylic acid is a higher priority functional group, so the amine becomes 3-amino propanoic acid. So this is the first carbon, second, and third, which explain the 3-amino propanoic acid. Likewise, between amine and alcohol, the hydroxyl is of a higher priority functional group. Okay, then same thing here. The benzoic acid is definitely a higher priority group. Okay, so that's how we came up with the naming. Now, quaternary ammonium salts are the organic equivalent of ammonium compounds like NH4+, where you have 4 alkyne groups bonded to the nitrogen atoms, alkyne or aryl groups. So we have ammonium chloride, or tetramethyl ammonium chloride. Tetramethyl means you have 4 methyl group. Okay. Like this. So this is tetramethyl ammonium chloride. Okay. Cyclic amine do exist. Here are some examples. pyrrolidine, piperidine, and choline. Right here, I just have some examples for you. Some naturally occurring amine include caffeine, nicotine, serotonin, morphine. Now, this is a simple exercise to help you determine the structural formula of the compounds and classify them, like this one, 1,6-hexyldiamine, because you have 1, 2, 3, 4, 5, 6. So there are 6 carbon in the continuous carbon chain, which makes it a hexane. And there are 2 amine on each end, 1,6-hexyldiamine. Okay. The amine is the substituent. And the nitro here is the substituent. So we name this 2-nitrophenylamine. As for this compound, we have the methyl group attached to a second and 4th carbon in the cyclic structure. So we call it 2,4-dimethyl cyclopentyl bracket amine. And here we have the methyl attached to the nitrogen instead of the cyclic structure. So we call it dimethyl cyclopentylamine. 1, 2, 3, 4, 5. So it's 5. Okay. Now, the nitrogen atom of most amine looks like ammonia, is sp3 hybridides. What is the shape of ethyl amine molecule with respect to the nitrogen atom? So around the nitrogen atom, we have 4 electron pairs, and they must be directed in a tetrahedral manner to minimize repulsion. There are 3 bond pairs and 1 lone pair. The shape of the amine molecule is trigonal pyramidal with respect to the nitrogen atom. Amines are polar molecules with a net dipole moment. The lower aliphatic amine are gases or low boiling liquids, low boiling points liquid. Okay. So for primary amine, the boiling point increases with increasing size of electron cloud. And here is the reason. We have larger and more polarizable electron cloud, which increases the size of electron cloud of the molecule. This increases the ease of polarization of electron cloud. That increases the strength of ID-ID interactions. Okay, please have all these points when you are required to explain the increasing melting point down the series. Among the isomeric amines, the boiling points increases in the order, with the tertiary amine having a lower boiling point than the secondary and the primary amine having the highest. For the primary amine, the main forces of interactions include ID-ID and PD-PD and hydrogen bond. For the secondary amine, the boiling point is lower because the molecule is less polar than the primary amine. Hence, the PD-PD forces are weaker. For the tertiary amine, hydrogen bond doesn't exist. So the boiling point is lower. In general, amine have higher boiling point than alkanes of similar size of electron cloud due to the presence of hydrogen bond being the predominant intermolecular forces. In general, amines have lower boiling point than alcohol. That is because nitrogen is less electronegative than oxygen atom. Therefore, the NH bond is less polar than OH bond. So the NH hydrogen bond is weaker than the OHO hydrogen bond. Amine form hydrogen bond with water. The lower members are very soluble in water because they interact with water molecules via hydrogen bond, and they have relatively small non-polar hydrocarbon chain. However, with the higher members, their solubility decreases because they have large non-polar hydrocarbon portions. The borderline solubility in water reach at about 6 carbon atoms. As for the smell, they are similar to a fishy character. They are found in rotting fish like dimethylamine as well as trimethylamine. We have butane 1,4-diamine and pentane 1,5-diamine found in decaying animal flesh. All right. So this is an interesting article on why do fish smell when you buy them. It's because of the amines compounds in them. Yeah, the fishy smell that is very unpleasant. So people actually use lemon juice to neutralize the amine, which is alkaline base. You do not need to know the reason for the sting. You just need to know there is amine there that will do. The aromatic amine doesn't make it smell nice. It means it does have a certain distinct smell or odor. They are liquid or solid with high boiling point, but they are toxic. For example, phenylamine is only sparingly soluble in water because of its large hydrocarbon portion due to the benzene ring. And it is quite soluble in non-polar organic solvent. So phenylamine is capable of dissolving in fats, which means that they can be absorbed through the skin easily. The basic strength of amine depends on two factors: how available is the lone pair of electrons for coordination with a proton, and the ease with which the protonated amine can undergo solvation with the water molecules and become stabilized. We will focus on factor 1, making use of it to account for the relative basic strengths of amine. So in general, basicity of amine increases in this order in gaseous phase. So the more substituent the amine has, the more basic it is. So the tertiary amine is the most basic, followed by secondary, primary ammonia, and phenylamine. And amine, like ammonia, is a Lewis base, which means it's an electron pair donor because it has a lone pair of electrons available on the nitrogen atom to donate to electron pair acceptor like your hydrogen ion. For example, amine in gaseous phase react with gaseous HCl to yield a salt as shown on the right, alkyl ammonium ion. So the amine actually donates its lone pair of electrons to the partial positive hydrogen atom in HCl. And this causes the HCl bond to break because Cl being electronegative than hydrogen is able to pull electrons to itself and cause the bond to break easily. So a volatile amine such as ammonia can produce dense white fumes of NH3 plus Cl minus with hydrogen fluoride. All right. So this is a dense white fumes. What will be observed? Now, if you want to rank the basicity of methylamine, dimethylamine, trimethylamine in increasing order of basicity in gaseous phase, we will have the tertiary, of course, having the highest basicity, followed by the secondary, as well as the primary being the last one. So the more R group, more electron donating group it has, the more basic it is. So the basic strength of each compound depends on the availability of the lone pair of electrons. So from CH3NH2 all the way to trimethylamine, right? We will see that there is an increasing number of electron donating alkyl groups. So the electron density of the nitrogen atom increases from methylamine all the way to trimethylamine. which make the lone pair of electrons increasingly more available to donate to a Lewis acid. And amine like ammonia is a Bronston-Lowry base, which means it is a proton acceptor because of its availability of the lone pair of electrons on the nitrogen atoms that can form dative covalent bond with the proton. For example, the amine can react with water to form OH-. So the water here is the Bronston-Lowry acid. The aqueous solution of the amine is therefore alkaline as it turns red litmus paper blue, because the solution will contain some excess OH- ion, but it's not a strong alkaline, okay? And amine can react with acid such as HCl to produce a salt shown on the right. So the amine gains the proton while HCl loses the proton. Hence, an amine like ammonia can produce salts with aqueous acid. And amine can also react with a weak acid such as ethanoic acid to yield a salt shown on the right. Now, amines are relatively weak base. Each amine has its characteristic base dissociation constant Kb. So, the Kb of an amine is a measure of the basic strength of the amine. It is a measure of the extent of ionization of amine in water. The larger the Kb value, the stronger is the basic strength of the amine. The smaller the pKa value, the stronger is the basic strength of the amine. So in this case, C6H5NH2 is the least basic, while CH3CH2NH2 is the most basic. Looking at the Kb value. And the reason has to do with the substituent, all right? Now, arrange the compounds in increasing Kb value and explain the order. So this is similar to the earlier example. So as we have discussed, the larger the Kb value, the stronger is the basic strength. So the highest one should be the ethylamine, followed by ammonia, and then phenylamine. So the basic strength depends on how available the lone pair of electrons on the nitrogen atom is, because that will affect whether it will form a dative covalent bond with the proton, as shown earlier. The greater the availability, the stronger is the basic strength. So let's do the comparison, the complete explanation. Ethylamine is a stronger base than NH3. Ethylamine, the CH2CH3 ethyl group is electron releasing or electron donating. So this will help to increase the electron density of the nitrogen atom. Therefore, the lone pair of electrons become more readily available to form dative covalent bond with the HCl or water with the Bronston-Lowry acid. Okay, basically coordination to a proton than that compared to ammonia. As for phenylamine, why is it weaker base than ammonia? It's because the lone pair of electrons of nitrogen becomes delocalized through its interaction with the pi electron cloud of the benzene ring. So this delocalization will make the lone pair less available for coordination to a proton compared to ammonia. Okay, so there's a good overlapping between the p orbital of nitrogen and the pi electron cloud system of the benzene ring. That will facilitate better delocalization of the lone pair electrons. Now, arrange the compounds in order of increasing Kb value and explain the order: phenylamine, 4-nitrophenylamine, and 4-methylphenylamine. So the larger the Kb value, the stronger is the basic strength. So the given compounds can be arranged in the order of increasing Kb value. So it really depends on how available the lone pair are, because it is the lone pair that actually reacts or form dative bond with the proton. The basic strength of the compounds depends on how available the lone pair is, as mentioned. So the greater this availability, the stronger is the basic strength. So we can see that this is the most available compared to this and then this. All right, so why this? Why 4-nitrophenylamine is a weaker base than phenylamine? So in 4-nitrophenylamine, the NO2 group is electron withdrawing. So it will decrease the electron density at the nitrogen atom of the NH2 group, making the lone pair of electron less available for coordination to a proton compared to the phenylamine itself. 4-methylamine is a stronger base because the CH3 is electron donating. That will increase the electron density at the nitrogen atom of the NH2 group to make the lone pair of electrons more available to form coordination to a proton. Now, how do we prepare amine in the lab? Alkyne amine in practice or principle are capable of being prepared by nucleophilic substitution by reacting halogenal alkanes with ammonia. So you're going to substitute the halogen with ammonia to form the amine. So for simplicity, this equation is used. We use concentrated NH3 in ethanol silk tube sheets. The NH3 acts as a nucleophile due to the lone pair electrons. However, the problem encountered with this method to prepare amine will be you will produce a mixture of products due to polyalkylation. So the use of excess ammonia is used to discourage polyalkylation. You don't want other products other than the primary amine to be formed. Okay, so why is it so? So what is polyalkylation? What is happening? So first of all, the ammonia with the lone pair of electrons will first attack the positive carbon. All right, and this bond will break to release the Br minus. Okay, Br is a good leaving group. Okay, and then the primary amine form itself is also nucleophilic. Okay, so it may undergo further reaction with ammonia to form secondary. It will. So the product here will react with ammonia to form primary amine. Okay. So this one would remove the H to form NH4+. So this primary amine becomes a nucleophile and attack the halogenal alkanes. Okay, so by similar equilibrium and further alkylation, eventually you have the tertiary amine and even the quaternary ammonium compound may be formed. Okay, so you have this one, continue attack, release, form back secondary amine, attack, release, then you form the tertiary amine, and then this attack, release, you form the quaternary ammonium salt. So the actual result will be a complex mixture of products. On an industrial scale, the products are separated by addition of alkaline to liberate the free amine, followed by fractional distillation. So if you use excess concentrated ammonia, the intended product will be the primary amine. If we use excess halogenol alkane, then we want to form the quaternary ammonium salt. So it depends on what you want. It's called polyalkylation because you are actually adding more and more CH3 lah. Yeah. This method is limited to the preparation of aliphatic amine because aryl halides will not undergo nucleophilic substitution with ammonia. So this reaction will not occur. So it's only limited to aliphatic. A filled p orbital of chlorine overlaps with the pi electron cloud of the benzene ring. So the lone pair of electrons on chlorine will be delocalized in the benzene ring. Therefore, CCl acquire partial double bond character, and this bond is strengthened and not easily broken. Other ways of preparing amine include reduction of nitriles, RCN, using our favorite lithium aluminum hydride and dry ether, or just using hydrogen with nickel and heat. Okay, that will do as well. Or we can start from amide using the same reducing agent to form the amine. Okay. So the CO group will be reduced to CH2. For simplicity, the reagent condition is usually written as LiAlH4 in dry ether. So just put 4H here will do, then form water. So 2H come here, the 1O come out, and form water with the remaining 2H. It can also be done on secondary amine as well. Doesn't matter because the amine part is not affected in this case. Tertiary amine also can, since this part is not affected. It's only this part that is reduced. Okay. Other methods include hydrolysis of secondary and tertiary amides. We can't produce amine from hydrolysis of primary amide. It will form ammonia instead. Okay. So this is secondary amide where you only have one H. Tertiary means no H to the end. Or it can be from basic hydrolysis, where you will start from tertiary amide. Okay, you release this part. Or acidic hydrolysis, but then the ammonium, it will form the ammonium salt, ammonium ion, which is protonated. Yeah. Because of the acid. When NaOH is added to the products of hydrolysis, okay, it will form a salt instead. Now, this method is used to prepare primary aromatic amine. So we usually start from, let's say, nitrobenzene, using thin concentrated HCl, heat under reflux, and followed by NaOH. All right, the NaOH is for the neutralization part. So you can actually, 2H come here, the other 4H come here with 2 oxygen. So in acidic medium, we have something like this. Okay, where the H is, then NH2 amine part is protonated. If we use HCl as the acid. But if we don't want to have this as the product, then we have to use alkaline so that it will be NH2 instead of the salt, because the amine can get protonated. Now let's start with the reactions amine undergo. Basically, we need to understand what amine act as in reactions. They are Bronston-Lowry base or Lewis base as mentioned earlier. They are also nucleophiles as discussed. So amine can act as Bronston-Lowry base or proton acceptor because the lone pair of electrons is available to form dative bond with proton. Both aliphatic amine and phenylamine form stable crystallized salts with mineral acids. So you can actually heat to evaporate off the water to form the amine salt. This is the neutralization reaction because amine is a base. Yeah. More examples for your reference. So the NH2 get protonated in a way, Cl minus, and you can heat to remove the water to produce the crystalline salt. Although phenylamine is not soluble in water, but upon reaction with acid, you can form a salt that becomes soluble. Okay, more examples. So secondary amine, tertiary amine also reacts as well. Doesn't matter. The amine can be regenerated from the amine salt by reacting the salt with alkaline. So we can reverse the process that will reverse back to get the amine that is there originally. Okay, the diagram below illustrates an experiment where acid is added to a solution of ethyl amine. So we may, okay, the solution of ethyl amine have a very characteristic fishy smell. And then you add your HCl to produce the amine salt. This reaction is exothermic, so temperature will increase. Exothermic because it's acid-base. The smell will disappear because the amine salt is non-volatile. So it doesn't produce the smell that you are familiar with. And then you add excess sodium hydroxide and the fishy smell returns because the amine is formed back. Suggest a simple chemical test to test for the ethyl amine ion, right? Yeah. The amine salt. Or you call it alkyl ammonium salt, right? Yeah. So the reagents and conditions will be sodium hydroxide and warm the mixture gently. So the observation will be a pungent smell. Ethyl amine is very fishy smell, but we describe as pungent. It will turn then litmus paper blue because it's alkaline. So what is the reason for this? So in an aqueous solution of the salt, right, this equilibrium exists. Okay. So the salt is a conjugate acid. So reaction with water form the hydronium ion. So addition of sodium hydroxide remove the H3O plus by neutralization. So the concentration of H3O plus will decrease and the equilibrium position will shift to the right according to Le-Chatelier principle. So more and more ethyl amine will be produced. Since it is soluble in water, warm the mixture will force more ethyl amine out of the reaction mixture to produce more ethyl amine that turn litmus paper from red to blue. Remember to warm the mixture. Now, some properties of amine and amine salt. So amine, they are not soluble in water, except for those with low MR. They are soluble in non-polar organic solvent, volatile, pungent odor. Adding with acid, you can form the amine salts, which are of different properties like high melting point, more water soluble. They are not so soluble in non-polar organic solvent and they are non-volatile, so there's no odor. That's why people add lemon juice to fish to remove the fishy smell. But if you add back alkaline, then the amine will be formed. So the formation of the amine salt can be used to isolate and characterize amine. So you also separate the amine from the neutral or acidic organic compounds. Because it is soluble, so it can be separated easily. The amine can undergo alkylation with halogenal alkanes, okay, with amine acting as a nucleophile. So this is the nucleophilic substitution mechanism. Okay. So the primary amine reacts with the one bromoethyl. Then you will form the secondary amine because this attract to this. So this one come out. Leaving group, Br leave. So it forms here. Okay. This is what happened. All right. Then we further okay, eventually you have the complete alkylation to form the quaternary ammonium salts. All right. Amines undergo condensation with acid halide or acyl halide to produce amide. Anhydrous condition is used because the acid halide can react readily with water. So you have the acid halide here with amine, you will form the amide linkage. Okay, it's a condensation reaction because a small molecule like HCl is removed. More example, so the acid halide can react with secondary amine as well to form the amide bond. So but with the tertiary amine, there's no formation of amide because there's no hydrogen from the acid, from the tertiary amine. So the type of reaction is called condensation. We have the acyl group, C double bond O. Then we have the ethanol group and the benzoyl group. Anhydrous condition used because the acid halide reacts readily with water. We form back the alcohol. Notes, amines are basic, so they undergo acid-base reaction with carboxylic acid to form a salt, but amide is not produced. Okay, just take note of that. It's different from acid halide. Now, give you an exercise, you can read the question first. Okay, so what is the structure of compound A? So the reaction between ethylamine and ethanoic acid is an acid-base reaction. So this is the chemical equation. You form a salt actually. And when warmed with sodium hydroxide, the pungent gas is produced. The pungent gas has to be ethylamine, which is basic. And you form a salt, a sodium ethanoate salt, and of course, you have water produced. So ethylamine is a base. It undergoes acid-base reaction with ethanoic acid to form a salt. And amide cannot be obtained when an amine react. They form a amine and a salt. So that will be formed instead. Now, let's look at the formation of 2,4,6-tribromophenylamine. So the bromination of benzene ring in phenylamine using Br2 occurs at room temperature without any Lewis acid catalyst. So it's quite reactive. So the type of reaction is electrophilic substitution using just Br2 at room temperature because it's super reactive. So it can have 2,4,6 substituted, sorry. This will be a white precipitate. The reason is because the NH2 is strongly activating and NH2 group is 2,4 directing. Okay. So the orange bromine solution added will be decolorized, and a white PPT of 2,4,6-tribromophenylamine is formed. Why is this reaction occur so readily? Because the NH2 group will help to increase the electron density as the lone pair of N is delocalized due to the group overlapping between the p orbital and the pi electron system of the benzene ring. So this makes the benzene ring more susceptible to electrophilic attack. Therefore, no catalyst in it, and you can substitute more hydrogen on the benzene ring. So it is a very useful test to distinguish phenylamine with other compounds. However, phenol also undergoes similar reaction and gives same observations. Take note that chlorine will have similar reactions as well. Now, phenol can react with nitric acid to form 2-nitrophenol and 4-nitrophenol. Can phenylamine react with nitric acid? Answer is no. Instead, because this is a base, that nitric acid is an acid, they will undergo neutralization. So this is not going to happen. What is going to happen is this one. It will have it will undergo acid-base reaction to form a salt. Now, other examples: formation of 2-bromophenylamine and 4-bromophenylamine. So to get a monobrominated phenylamine, is necessary to reduce the electron density and hence the reactivity of the aromatic ring in the phenylamine. Okay, so how can we do it? So this can be achieved by exhalation of the strongly activating NH2. So change it. Maybe you can use ethanol chloride, acid halide to produce the moderately activating group. Okay. So NHCOCH3 is actually 2,4 directing. So after reaction with aqueous bromine, the ethanol group can then be removed by hydrolysis using hot sodium hydroxide. You can also use acidic hydrolysis, but still need to convert to basic medium to yield back phenylamine. Okay, or else it will be protonated like NH3+, then you still have to add sodium hydroxide, troublesome. So the first step will be through this reaction called condensation. Then you will form this. All right. And then, because you want it to be 2,4 directing, right? Correct. So you have to change it to the activating group, which is 2,4 directing. Before that, it's not. NH2 is not. Yeah. For BR lah. It's different from just now the, yeah. If you want, it's just how if you don't do that, right? Then you got 2,4,6. But if you just want one of it to be substituted, you must have alkylation first. Yeah. No, I mean exhalation first. To convert this first. Okay. So this is hydrolysis. You can actually cut to form back this. Okay. So in summary, right, these are the preparation of phenylamine from nitriles, from halogenoalkane, from amide. Then for the reactions, there's quite a lot. You can form a salt with acid. You can have salt reactions again, amide, and more. Okay. This one is the, okay, so this is a good summary of all the reagents and conditions for all the reactions. For number 1, right, you use LiAlH4, dry ethyl, or hydrogen nickel as the catalyst heat. For 2, you use excess concentrated NH3 in ethanol, heat in silk tube. 3, you can also use converting amide to amine, right? Can also use the same reducing agent. Yeah. Then 4, you use dilute HCl, yes. And 5 is just a physical process to evaporate off the water. 6, acid, ethanoic acid, then you can actually form and it will get protonated lah. Then 7, you use acid halide lah. Yes. Then 8, you use benzoyl chloride. Yeah. Do they have it there? No. Also can. Then 9, you can use CH3CH2Br, 1-bromoethane. Yeah, it's alkylation, I think. Yeah. Heat in seal tube also to increase the chain. Nucleophilic substitution. Then you have you can actually use acid chloride again, acid halide again to, halogenate alkane, sorry, to further alkylation. Yeah. Okay. So we are done with amine and phenylamine. So for phenylamine, right, this is a summary starting from here. If you want to prepare this, you can start with a benzene using corn nitric acid, corn sulfuric acid, 55 degrees Celsius to form NO2, and then use the reducing agent, from this one. Another way is salt. You can actually form back this or this way, reverse, you can reverse the change. If you want to, the reactions of phenylamine can be, okay, you can further alkylation of it, right? So you can actually do this. Or you can add a acid halide from this, or reverse the process by hydrolysis. You break the amide linkage, right? Yeah, to form back the amine. Or with this one, the benzoyl chloride. Benzoyl ethyl chloride. Then you will form this one. This. And this one can be further. Yeah. It's a summary of the earlier one. Okay, we finished with amine and phenylamine. We move on to the chemistry of amides. So we talked about that just now, a bit of amides. So amides are primary, can be classified as primary, secondary, or tertiary, depending on the number of alkyne groups bonded to it. So you have only one here, that is primary. 2, secondary, then even the last H is substituted tertiary amide. To name the primary amide, first name the corresponding acid first. Drop the IC acid or OIC acid sulfites from the name of carboxylic acid and substitute with the suffix amide. Then secondary and amides are named by treating the alkyl groups on nitrogen as substituents, specifying their position at prefix N. So a cyclic amide is called the lactam. Okay, example caprolactam. But in terms of naming, we just call it okay. So this is acid, right? 1, 2, 3, 4, 5, 6. Hexanoic acid, 6. So this is the 6th one. So it's called 6-amino hexanoic acid lactam. Just an example. Then like we can like amide, we can say like methyl amide. We drop the IC acid, OIC, take out. then become, instead of metanoate, we call it methyl amide. Then ethane amide. Okay, benzyl carbosamide. Yeah, benzamide also. Okay, secondary amide. So for, you can just put prefix N nitrogen, N dash methyl propane amide, because 3. So N, because the substitute of nitrogen will just put N. That's how they do nomenclature. To the N, common N dimethyl ethane amide. So for physical properties, they are apolar organic compounds. They are crystalline solid with strong intermolecular hydrogen bond. So there's hydrogen bond because of the NH2. Compared to tertiary amide, first and second amide, they have higher melting and boiling point because of the presence of hydrogen bond. Yeah, but the secondary, the tertiary amide molecules, do not form hydrogen bond. So their boiling point is lower because there's no hydrogen atom directly bonded to the electronegative N atom. Lower member of aliphatic amide are soluble in water because of the hydrogen bond. But with increasing size of the non-polar hydrophobic hydrocarbon chain, the solubility decreases. Unlike amine, right? Amide are still base but very weak base. So we can just regard the amide as functional group to be neutral. So they are not going to change the color of the litmus. Why is that neutral? The lack of basicity is explained by picturing the amide as a resonance hybrid, being stabilized by resonance between structure 1 and 2. So the delocalization of the lone pair of electrons of nitrogen into the C double bond O group imparts a partial double bond character to the CN bond. So there's a partial double bond character. So it renders the amide linkage planar. Like here. Come here, come here, come here. Consequently, the lone pair of electrons or N will not be available to coordinate with the proton as in amine. So we can form amide by condensation of acid chloride with ammonia or amine. So the amides can be obtained from the reaction between ammonia, primary amine, or secondary amine with acid chloride at room temperature. So this is what we have covered under the reactions in carboxylic acid just before this. All right, how to prepare amide. So for the reactions involving amide, we have hydrolysis to come first. So it basically, hydrolysis is the opposite of condensation. All right, so you cut, you form back this and this. You put back the OH and H respectively. That's it. Very straightforward. The reaction can be used to distinguish amide from others. So what is this reaction? So you can use sodium hydroxide, strong heating. So what happens is that you're going to form your favorite ethyl amine, the pungent fishy smell, and it's also alkaline. So this bond, this amide linkage is broken. And then you form O minus, this one form back the ethyl amine. Yeah. This test will work if the amine produced, right, have 5 carbon or less, because these amine are volatile enough. So it will only work with 5 carbon or less due to the volatility. Okay, let's look at one example. The diagram shows the structure of tetrapeptide B, peptide bond. Okay, so when 0.1 mole of T is heated, how many moles of sodium hydroxide will be react? How many moles? So you have 1 here, 1 here, 1 here, 4. You also can 5, 6, and 7. So it's 7 times. AMITES undergo reduction to form amine using lithium aluminum hydride and dry ether. Okay, so we cannot use sodium boron hydride or even hydrogen to reduce amide. So in summary, right, amides are neutral. Amides are not basic because the lone pair of electrons on the nitrogen atom interacts with the high electron cloud of the adjacent C double bond O and is delocalized. So this lone pair of electrons is not available for coordination to a proton. So if we compare the basic strength of the ethane amide versus phenyl amide, ammonia ethyl amide, we have the amide being the weakest base. So this is a summary of the reactions involving our amide, ethane amide. It can undergo base hydrolysis, acidic hydrolysis, and reduction as well. Yep. Now, so these are a table that shows how you can use the various that shows a summary of the properties and the reactions and the observation to be made for the various amine 5C or less, amine 6C or more, phenylamine, amide, ammonium salts. So for amine, okay, we go and look at them one by one. They are liquid, high volatility, soluble in water, turn moist red litmus paper blue. With dilute acid, no observable change because amine is already soluble with HCl. Yeah. Though there's a reaction, but you cannot really see any observed or apparent change. Yeah. Then for sodium hydroxide, right? All right, you have you will form a pungent gas, the ethyl in it will be formed . Same for if you add aqueous sodium hydroxide and warm in boiling water bath, that will do as well. Test the gas, but this one will take a bit more time. Amine is volatile and leave the mixture on heating, so it will be alkaline, turn litmus paper from red to blue. For Br2, no observation, no change, no observed change. Solution remain orange for bromine. As for amine, similar, but the volatility is low and it's not so soluble because of the hydrophobic chain that's quite long. It will dissolve to form homogeneous solution for amine. No pungent gas. Amine is not volatile here. Solution will be orange. Same. Phenylamine, sparingly soluble, I would say. No pungent gas because phenylamine is not volatile. But with bromine, there will be a white PPT form and the orange Br2 decolorized. As for amide, the one we just went through is a solid of low volatility, soluble, and yeah, no observable change . And with NaOH, no pungent gas. Amides need stronger heating to hydrolyze to amine. So if you just add NaOH, cannot. Pungent gas evolve if you really heat it. Yeah. So if amine form and is volatile, oily, or there will be oily layers separate out if amine form is 6 or more C. Okay. Ammonium salt, both are actually not going to turn litmus paper. They are not really that alkaline. It's neutral actually. Okay, there will be a pungent gas if you heat or just add sodium hydroxide to it. You'll release the amine back. Yeah, the amine will be released. Okay, so this is a word example. Suggest a chemical test to distinguish the compound. Some tests may require preliminary breakdown of the compounds. So this is an amide. And this is another amide. But then, how do you approach this? So think about it, okay, before we move on. So for part A, right, the difference is the one that's bonded to the benzene ring. So if you hit both compounds very strongly with aqueous sodium hydroxide, hydrolysis will occur. So the NH2 form, the COOH and Na+. Then the other one will form this. So you need, that's why they say you need to have an additional reaction to separate out first. Okay, so 2 steps lah. So the phenylamine liberated in the first reaction, if you add aqueous bromine, it will decolorize it and form a white PPT, 2,4,6 tribromo-phenylamine, right? But for this one, right, this one, methylamine, right, there are no decolorization of the bromine solution. As for the second one, okay, ammonium salt versus amide. So we can warm both gently with sodium hydroxide and test the gas using moist red litmus paper. If you warm this, you liberate the ethylamine, so you can actually, it will turn litmus paper from red to blue and the pungent smell evolve. Yeah, NH2, then this one CO minus Na plus, and the water come out H2O, correct. As for the amide, right, it cannot be hydrolyzed into the amine by warm gently. No alkaline gas. No alkaline gas will be evolved. Yeah, amide cannot be hydrolyzed by warmly gently. So if you recall about, okay, the amide into the amine. You cannot warm gently. You have to warm, let me see, strong heating. It must be strong heating. So here is gently. It must be strong heating. Okay. In order to break the CN bond successfully. Okay, let's move on to the next concept. We finish amine, amide, and amino acids now. Amino acids are organic compounds that contain at least one amine group and one carboxylic acid group. So amino acids can be classified as alpha, beta, gamma, and so on, according to the location of the amine group on the carbon chain that contains the carboxylic acid group. So we have alpha, beta, and the gamma. Although we have more than 700 different amino acids known to occur naturally, a group of 20 of them commands special attention. Okay, how do you differentiate the alpha, beta, and gamma here? Alpha is the location of the amine group. So this one is the one that's directly to the acid, so it's alpha. The one away is the beta. 2 more away, gamma. Okay. Yeah. So all the 20 amino acids from which proteins are derived are actually alpha amino acid or 2 amino acids. So the amine group is attached to the alpha carbon atom. Our focus will be only on the alpha amino acids due to the time we are allocated to study the syllabus. All right. So these are the basic building blocks of proteins. They differ only in the substituent R attached to the alpha carbon. Okay, so let's go through the nomenclature of the amino acids. Like the first one, amino ethanoic acid. Okay. 2-amino propanoic acid. Second ma. 2-amino 3-phenyl propanoic acid. 2-amino butane dioic acid. 2,6-diamine hexanoic acid. Okay. Amino acids may be classified as either neutral, basic, or acidic according to the number of amino and carboxyl group they contain. Okay. Yes. For amino acids, let me see. You don't have to memorize every single amino acids, but you need to understand how to name them. Okay. The understanding is more important than memorize for the amino acid part. There's quite a lot of concepts here to be covered. Okay. So they're either neutral, basic, or acidic, depending on the number of amino and carboxyl group they contain. The neutral amino acid contain equal number of amino and carboxyl group, usually one of each. The basic amino acid contain extra amino group. The acidic amino acid contain extra carboxyl group. So the structure of the 20 amino acid commonly found in protein are shown below. Okay, so basic extra amino, acidic extra carboxyl. Okay, that makes sense, right? Neutral means equal number. Okay, so glycine, we have an extra, it's about 6 lah. Yeah. The PI is about 6. Largely because there's one carboxyl group and one amino group, right? That's why it's almost neutral. But amino acid being amino acid is still considered, should I say, acidic. Yeah, but very acid. So PI is just a value to indicate the global acid or zwitter ionic compound. We'll talk about that in detail later. Something like pH, but not exactly. It's called isoelectric point. It's used for a protein and peptide one, actually. Yeah, it's like the pH lah. Okay. This one also about the same. Yeah, the circle part is just telling you the difference in the R group lah. Yeah, the difference is only in the R group. Here, there's a bit more acidic already because of this. Yeah. Something to do with the R group. Okay. Then with polar side chains. So these are the non-polar side chains. For polar side chain, we have this, this. Okay, more examples. With acidic side chains, very acidic, no? Aspartic acid and glutamic acid. You have extra COH. And this one, you have the extra NH amino group, makes it alkaline. Okay. So these amino acids are not synthesized by the body, so they need to be provided in our diet. So let's look at the physical properties of the amino acid. With the sole exception of glycine, amino ethanoic acid, two amino acids contain at least a chiral carbon atom and displays an enantiomerism and exist in optically active form. Okay, so they are mirror image. So they usually are racemic mixture and then they are optically inactive for the one in the lab. But the one usually from natural sources, you have purely one of it only. So it's optically active. So it depends. Okay, Zwitter ion. We commonly write amino acids with intact carboxylic acid group and amine group. The actual structure in a dry solid state is Zwitter ionic. That is the correct way of representing it. And it's a dipolar ion. But it is not an ion, but it's an electrically neutral molecule with oppositely charged ends, so it neutralizes each other. The amino acid undergoes internal acid-base reaction where the carboxylic acid group loses a proton to form a carboxylate ion, and the amine group is protonated to an aminium group. All right. The Zwitter ionic nature of amino acid gave them some unusual properties as described below. So these are some weird properties because of the Zwitter ion. The amino acids, right, they are crystalline solid with high melting point. In solid amino acid, the lattice particles are Zwitter ions held by strong ionic bond. The strong electrostatic FOA between the opposite ends of the neighboring Zwitter ions requires a large amount of heat energy to overcome, which explains the high melting point, electrostatic force of attraction. And amino acids are much more soluble in water because the opposite end of the Zwitter ions interact with water molecules via ion-dipole interactions. So this causes the amino acids to be more soluble in polar solvent compared to non-polar organic solvent like benzene. Amino acids are less acidic compared to carboxylic acid and yet less basic than amine. So the acidic part, right, is actually lesser. The NH3 plus is lesser than the COH, and the Kb of the COO minus is actually lesser than the Kb of NH2. Amino acids are amphoteric. They have both acidic and basic properties because they have both acidic and basic groups now. So it can act as a Bronsted-Lowry acid with the CO2 minus to react with the OH minus. Oh no, sorry. This one will react. So you have the OH minus is protonated. So acid donates the proton over. Donates a proton. As a Bronsted-Lowry base, it will accept the proton. Okay. For simplicity, right, assume that the R group is neither basic or acidic. So we just can write the equation like this. All right. Okay, something like this will happen. So for glycine amino ethanoic acid, right, the Ka of the NH3 plus is 1.6. Kb is 2.5. So since Ka is larger than Kb, the glycine is weakly acidic. Okay. Now, this is something that we have talked about, that PI, isoelectric point of amino acid, that is used for amino acids. The isoelectric point of an amino acid is defined as the pH where the amino acid exists predominantly as zwitter ions and does not migrate under the effect of electric field. So at the isoelectric point, pH equals to Pi, zwitter ion concentration is at the maximum. So each amino acid has a characteristic isoelectric point. The differences in isoelectric points can be used to separate mixture of amino acid by electrophoresis. So in aqueous solution, the predominant form of amino acid depends on the pH of the solution. So in a basic solution where pH is greater than Pi, the predominant form will be anion. Okay, so there will be a net migration of the anionic form of the amino acid towards the anode. Isoelectric point, zwitter ion, there will be no migration. Acidic solution, the dominant form is the cation. There will be a net migration of the amino acid towards the ketone. Okay. Now, electrophoresis, right, is a technique to separate and analyze a mixture of amino acids or proteins by observing their migration under the influence of the strong electric field. It is a technique that combines principle of electrolysis and vapor chromatography. So separation can be effected because amino acids have different isoelectric points and different rate of movement due to different sizes and different net charges. So a mixture of alanine and aspartic acid, lysine, right, can be separated by vapor electrophoresis. Okay. So a streak of amino acid mixture is placed at the center of a piece of the filter paper wet with a buffer solution of known pH. The buffer solution is of a pH chosen to yield the maximum separation of the amino acids. So we have two electrodes here placed in contact at the edges with a potential of several thousand volts. The amino acids then migrate in the electric field at a speed which depends on their charge to mass ratio, the position of the various amino acids detected by ninhydrin. With the exception of proline and hydroxylproline, all the two amino acids react with ninhydrin to give a violet colored product. So aspartic acid with a pH of 2.8, the predominant form will be anion. So it will move towards the anode. Alanine, zwitter ion, no migration. Lysine, cation, because the pH is 9.7, it will move towards the ketone. So that's how you separate the proteins. Amino acids consist of COH and NH2 groups. So they undergo similar reactions like carboxylic acids and amine. So for the amine part, it can neutralize acid and undergoes condensation reaction with acid chloride to form amide. For the acid part, it can neutralize base and undergo condensation reaction with alcohol to form ester. So acid-base reaction, neutralization, we can have like the amine part, right, reacts with the acid to form, the CO minus, the conjugate base. This will react with this to form COH. Okay, and releasing the Cl minus. For the base, is this part here to form the, yeah, this one and this part here, Na plus and NH, H2O form. H2O, okay. The amine group in the amino acid can also react with acid chloride to form amide, all right? Esterification, very similar to carboxylic acid with the exception that the mineral acid catalyst ultimately will react with the NH2 group. Yeah, like this one. So once the ester form, it will react with HCl to form this. Okay. Okay, peptide formation. So how do dipeptide form? So you have undergo condensation releasing water. So you have C double bond O. This part here, we have this one here. So you have this form. Water release. I think this part here. Yep. Dipeptide with one peptide bond. The product is an amide called a dipeptide because it consists of 2 amino acid residues. The amide linkage between the amino acid residue is called peptide bond. So, yeah, for amino acid, we don't really call it amide, but we call peptide because, yeah, that's for protein normally. So a peptide bond or peptide linkage is the name given to amide bond or amide linkage form between the alpha NH2 of the alpha amino group and a COH of another alpha amino acid. So if there are 2 amino acids undergo condensation, dipeptide, 3 tripeptide, 4 tetrapeptide, many just polypeptide. So a peptide is a compound containing 2 or more amino acid residue linked by peptide bonds between the amino group of each amino acid and the carboxyl group of the neighboring amino acid. So in general, amino acid form peptide, peptide form polypeptides and proteins. So they are macromolecules. So proteins are basically polyamides. Proteins are compounds with more than 50 amino acids containing 1 or more polypeptide chains. The terminals with the free alpha NH3 plus group is known as the N terminals. The other side is called the C terminals. Okay. Yeah. By convention, a polypeptide chain is drawn from the amino N at the left to the carboxyl and C terminals at the right. One repeating unit. Because the primary sequence reflects the relative positions of the residue linked together by peptide bonds, peptides containing the same amino acid residues but in different order are not identical. For example, prolys and lysine, they're actually different. Okay, so the sequence will matter. So prolys represent a dipeptide with proline at the N terminals. Pro will be the dipeptide with lysine at the N terminal, so different. So to draw the structural formula of tripeptide, alanine and phe, then you just, okay, what you do is just you break that, treat it like hydrolysis, all right? NH3 plus, CH2, then C, double bond. Should be double bond here. Double bond here. Then you form the NHC, let's double check, double bond. NHC, C. Yeah, it should clear right. The other end, the N terminal and C terminal, just put this, little ion. Okay. All other possible isomers, just play around with the number and get a number and get it. Okay. The sequence of amino acids in peptide or protein can be analyzed using various techniques. So we can use complete hydrolysis. With completely hydrolyzed protein, will give the number of relative amount of different types of amino acid. However, it doesn't tell me the order. So we will do partial hydrolysis, which give us smaller peptide fragments, which retain some sequence information. When these fragments are separated and identified, the overall amino acid sequence can be deduced from the overlapping of the peptide sequence, like pieces of jigsaw puzzle. So polypeptide, peptide, and amino acids. Okay. So you can use acid-based catalyzed hydrolysis of peptide bonds or enzymatic hydrolysis using a suitable enzyme to do this. The peptide bond is cleaved upon heating or in the presence of acid or alkaline. So the cleavage is not very selective. So it will lead to a mixture of short fragments cleave at different positions. So these are the few ways of doing it. Okay, so just to take note, if you want to have complete hydrolysis, right, or do it at concentrated HCl with high temperature 100, 120 for 10 to 36 hours in an evacuated tube. Partial hydrolysis of the hexapeptide with the composition gave the following fragments. What is the structure of the hexapeptide? How to go about doing this is you can have, okay, so these are the fragments, gly, pro, arg. So you find those that are common law. Okay, so this one is the one that is common, pro, and this one. Pro not really, because pro has one in the middle, right? Yeah. So you will take pro, this one, to here. And then this one link to this one. Right? So this is the fragment. Then this one, this one. Okay? So it will be pro, length, gland, pro. So you just play around with the fragments lah. Okay, another exercise. Aspartame is a dipeptide derivative used in artificial sweetening agents. Its general usefulness is restricted because it loses sweetness after hydrolysis. Okay, so what products will be formed after prolonged acid hydrolysis? So if you allow it to break down, what happens is that everything prolonged means everything break law. So you will have this one break. Okay, because it's acid, so this one will be no Na plus acid ma. Wait, then this one. This one break. Then this one also break, right? Yeah. The ester linkage also break. Yeah. Okay. I'll remove this. Okay, next one. Enzymatic hydrolysis. For peptide containing more than 50 residue, chemical hydrolysis is not practical because you will lead to many unwanted side products accumulating. So enzymatic hydrolysis using enzymes known as protease, peptidase, they are selectively hydrolyzed specific peptide bonds only. Okay? So for example, trypsin, right, only catalyze the hydrolysis of peptide bond at the carboxyl end of the basic amino acid, arginine and lysine. So they only cut here. So it's very specific lah. Okay. Now, so now we are moving on to the appendix already. We are done with the syllabus. So this is just extra information on the previous concepts we cover. All right. Like how do you prepare phenylamine in the lab? You can use nitrobenzene using these conditions. How do you do it is, okay, I think this is just for your information. You don't have to, memorize the specific equation, but just to understand how it goes. Okay. Then but this is important about the titration curve of the protonated amino acid. So you have 2-amino propanoic acid. Okay, it's considered to be dibasic acid. Okay, with 2 pKa value. Okay, so it can donate 2 protons during its complete titration. So in step 1, you can have reaction with OH minus. Then you have can remove the protonate, this one, remove this one. And then once the zeta ion form, reacts again to remove this H. So the graph shows the titration curve for the protonated alanine. The pKa1, pKa2 are far apart, such that 2 equivalent points can be seen more obviously. The first equivalent point corresponds to the completion of reaction 1, while the second corresponds for reaction 2. Okay, so this is the question. So at pH, which is the initial pH, right? The predominant species, because it's acidic, so it's NH3, fully protonated. Reaching 2.3, you reach a point where you have a mixture of this one and this one. So there's a buffer solution of the maximum buffering capacity, where the cation is equal to the concentration of the zeta ion. These two. When it reaches 6, right, that's where pH equal to Pi. Then you have zeta ion. The first equivalent point of titration is reached. Yeah. pKa equal to pH. When pK2 means that the buffer solution of maximum buffering capacity, then you have if a mixture of the zeta ion equals to the anion. Yeah. And this is just a synthesis which you can just read yourself to form the amino acid. Okay, that's it for today. Hope you enjoy the lecture. Remember to subscribe to my channel. Thank you.